All right, good afternoon, everybody. Let's get started. For announcements, homework 5 is posted, so take a look at that. I think that's not due until the end of next week, but take a look at the due dates and due times on Canvas for all the assignments. Lab 7 will start this week. This week, we're going to be working on integrating the sensors that you got working during the last lab. We're going to integrate that code and that hardware in with the constant speed propeller code. So that's coming up this Friday. So during the previous class, we talked about developing code for the microcontroller, that process for doing that. We talked about microcontroller pinouts, and we talked about digital ports. So today I want to continue talking about microcontrollers, and we're going to talk about microcontroller pin configuration, especially for the ports, and logic voltage level shifting. So when you have logic circuits like microcontrollers, other circuits, sensors that have different logic levels, 5 volts, 3.3 volts, for example, you can insert level shifters in between, and I'll show you what that looks like. And we'll also start on analog to digital conversion, which is a very useful way to use a microcontroller with analog inputs to, again, sense and control. Okay, so we're going to go back and look at really quick. Last time we talked about the pinout of the Arduino board. And this board, it's typical of development boards or evaluation boards where you have headers where you can access signals. There's a microcontroller with supporting electronics, so you don't have to do much to get the microcontroller running and program it. So so there are other development boards for other microcontrollers and other Arduinos that have similar diagrams. You'll usually see the pinout of the board and the pinout of the microcontroller, and you can get access to the digital ports and the analog ports, analog inputs, and other peripherals of the microcontroller. Okay, so let's talk about configuring the digital ports. And I want to start this off using a clicker question. So grab your clicker applications. Okay, so general purpose I/O ports, GPIO, allow the microcontroller to sense digital inputs and then produce voltages on digital outputs. And on this microcontroller, the Atmega 4809, the GPIO port implements up to 8 bits of digital I/O per port. Okay, and so you can control the ports using the peripheral registers. Peripheral registers are essentially memory locations inside the microcontroller that you can write bits in software to control those locations. And that's how you control whether a port is a digital port or an analog port or an input or an output. So you write to these registers to control whether a digital port will be an input or an output or other configuration options. So let's bring up a data sheet. So here is a half a page of data sheet here. This section of the data sheet describes the data direction for a digital port. So you can see this name is DIR. That's just an abbreviation or a way to describe this data direction port. Okay. And so what you do is you see this, you have this table here and then some description below, but you have 8 bits here. So bit 7 down to bit 0. You can read or write to each one of these bits, right? So you can read what the state is, or you can write values to this. And on startup, the reset value, all of these values, these bits are set to 0 in this data direction port. So the data direction port field describes, controls the output driver for each port pin. So if you want certain pins of port A, for example, to be outputs and certain pins to be inputs, that's what you set here. And so if you set each one of these bits, or any one of these bits, to a value of 0, then that associated port bit is configured as an input-only pin. And that output driver is disabled. So if you remember back to the block diagram I showed you, the structure of digital port pin. I had a block diagram. I showed you a flip-flop and a buffer and different values in there, different components behind that pin. Well, the output driver is disabled when you want to use this port pin as an input. And then if you set that value of any one of these bits to 1, then that associated pin is configured as an output and the output driver is enabled. Okay, so you set values to 1 to be an output, values to 0 to be an input. So the question is, what hex value should be written to port A.dir? So this is a way to access this byte in the Arduino code. Okay, so you're controlling the direction of each bit of port A, each of the 8 bits. But what value in hex will cause the following digital port directions? So you want to use bit 7 as an output, bit 6 as an output, bit 5 as an output, bit 4 as an input, and so on, right down to bit 0. So you're going to use all of these bits of port A, but some of them as outputs and some of them as inputs. And here's how the byte, the word, the 8-bit word, is organized. Bit 7 on the left, bit 0 on the right. Okay, so let me start up the clicker app here. So what value should you use? Which one of these values should you use to set these directions for port A? Okay, so we know, so bit 7 is an output, so we want that value to be a 1. Bit 6 is an output, we want that value to be a 1. And you can so on figure these, fill in these values, 1, 1, 1, 0, 1, 0, 0, 1, to correspond to the inputs and outputs for the direction. Okay, so now you've got to convert that to hex. And I think the easiest way to convert from binary to hex is start all the way on the right, take the value 4 bits at a time. So convert 1001 to, I do it first to decimal. So that's 8 plus 1, that's 9 base 10. And that's also a 9 in hex, 9 base 16. And then 1110 is what? 8 plus 4 plus 2, which is 14 base 10. That's an E in hex, E base 16. So you get E9. So if you program E9 into this register, port A.direction, then you will set those pins as inputs and outputs described here. Okay. All right. Let's see. Now, in the code, in the Arduino code, you could say port A.dir equals E9, like I said here. You could also express it directly in binary in this compiler, in this code. So you could write out the whole value, which is just more digits, right? Or you could even specify the value in decimal. So this value 11101001 is 233 in decimal. So you could say any one of these will work, but going from, you could use binary. That gets a little tedious if you had a 32-bit word you had to type in binary, and you know the value you want in hex, you could use a lot fewer digits, a quarter of the number of digits. It's a little more tedious to look at 233 and try to convert that to binary and try to see which bits are set. So I often use hex. That's probably the most of the time I use that. And sometimes I'll use binary if I'm changing individual bits. Okay. And if you have any questions, just shout them out. We can talk about them or shoot them in the chat. Okay. All right. So let's continue on. No, that's not what I wanted. Talking about digital ports in Arduino code. So the Arduino language that you're writing into the IDE, into the text editor, is actually a subset of the C language standard library, right? It's a lot of it. There are some C standard language statements that are missing that I've noticed in the past. But the Arduino also provides additional functions to simplify configuring and using the ports. All right, so for what we just talked about in the clicker question, where you have to go in and figure out the hex value and write the value to the correct register, and then kind of make sure you have the other figures, the other settings configured for the port. You can just use these functions, and these are the functions that you use for controlling digital ports in the Arduino code. So you have pin mode, and this configures the pin to behave as either an input or an output. So this is changing those bits, right? This is going in and actually changing those bits in that memory location, in that register, to change the pins to be either inputs or outputs. Okay, then you have digital read. So if you have a pin set to an input, then this will read the value from that digital pin. If you have the value in the register set for a pin to be an output, then digital write will write to that, either high or low as you specify. So you can tell it what value to use. You see these input arguments here, like input output or input pull up. These are actually values that are defined by the code. So when you go in and you select what microcontroller you're using on the board, what kind it is, the compiler goes, the IDE goes and grabs some of the code that sets these values, right? So when you see input output and input pull up, those are values. High or low is 0 or 1. You could use 0 or 1 if you want as well. All right. So here's a digital port output example in the Arduino language. You have setup and loop. So what I usually do in setup is that's where I set the pin mode. I want pin 10 to be an output. And then in loop, if I want to make that pin alternately high and low, here's a digital write to pin 10, make it high, and delay 1,000 milliseconds, about 1 second. I say about 1 second because it takes some time to execute these statements. And then I have digital write to pin 10 as a logic level low, and then delay. Okay, so this is going to make this pin right here alternately high and low roughly every second. Pretty close to every second, except for any time it takes to do things behind the scenes in between loop runs here. So that's an output example that shows you how to set the mode and write to a pin. Here's the digital port input example. So in setup, I've actually set 2 pins here. Pin 7 is going to be an input, and this pin associated with LED built-in is going to be an output. So often these Arduino boards have an LED, one of the LEDs on the board, connected to a digital port so that you could blink the LED. It's good for troubleshooting. It's often good to blink an LED to see your program is running, or you can debug using that. Well, each Arduino board has a different pin number of the microcontroller attached to the LED. So when you define which microcontroller you're using, or I should say which board you're using, this LED built-in might be set to, pin 10, pin 11, whatever the value is. But then you don't have to remember it. You don't have to look it up. It's already defined for you. Okay, so that sets up one pin as an input, one pin as an output. Here I declare a variable to read the pin value. So let's read pin 7, because pin 7 set up as an input. Let's read that state. And then let's make the LED state equal to the pin value. Okay, so that's just an example of input or reading and writing again. Okay. And so if you measured pin, or if you applied a voltage to pin 7, then 0 volts or 5 volts for this, in this case for 5-volt logic, you would be reading that pin. So the Arduino language functions handle setting those microcontroller registers. You can go in and set those registers manually. There are defined pound defines that are defined for the register locations, and you can go and change those bits at a low level, but you can also use these functions. At power up, the default state of each input is, or of each port is input, which means high impedance. So those ports have high impedance, which makes it look like a very large resistor between that pin, let's say that header pin, and ground. Now this pull up here, right, input, output, and pull up, if you set a port mode to input pull up, then that's effectively connecting a fairly large resistor value between that pin and VCC, okay, the 5 volts of this microcontroller. And those resistor values are somewhere between 20K and 150K, depending upon the board, depending upon the microcontroller. And what that lets you do, if you remember when we talked about switches in a previous lecture, I said one way to interface a switch, like a push button, to a microcontroller so you could read the state of the switch, is to have the switch basically connected between a pull-up resistor and ground. So when you press the switch and you close the switch, there's a pull-up resistor there to hold the value high, the voltage high, until you press the switch, close the switch, and the value goes low, the voltage goes low. So instead of using an external resistor, you can use an internal resistor to the microcontroller. This will internally be pulled up. So saves you some space in your circuit. As far as a limitation, for each digital output port, remember there's a maximum source or sink current defined for a microcontroller. In this case, it's pretty high, 40 milliamps for each port. And also there's a total for all ports combined. So take a look at that in the datasheet if you start trying to source a lot of current from digital pins. So that's a useful takeaway if you wind up sourcing a lot of current. All right. Okay. So let's look at an example, logic signal voltage level shifting. So let's say that you have the sensor, you have a humidity and pressure sensor, and you want to connect that sensor to the microcontroller. So here's a humidity and pressure sensor right here. It surface mounts to a board. And so you have this microcontroller board, and here's the sensor. Here's a block diagram of the sensor. And the interface between the microcontroller and the sensor uses digital signals. It might use I2C or SPI, serial peripheral interface. Okay, so there's a serial data connection between the sensor and the microcontroller. And let's say the humidity sensor uses 3.3 volt logic. So a 1 is nominally 3.3, a 0 is nominally 0 volts. And the microcontroller, though, uses 5 volt logic. Okay, so you have two different logic families you're trying to interface. And you look at the data sheet, and the limitations of the sensor show that the interface voltage range is 1.2 to 3.6 volts. So if you apply 5 volts to the digital sensor input, you will likely damage that sensor. So if you're sending these bits over the interface, over this digital signal interface, then you apply 5 volts, probably going to damage the sensor, right? You have this boundary, 3.3 volts on one side, 5 volts on the other for logic levels. So you got to do something here. So let's use a logic level shifter to translate between 3.3 and 5 volts. A really clever way to use a FET, right, here's a MOSFET here, to be a bidirectional level shifter is to do this. This is that circuit. And this circuit is cool because if the left side, A3, right, that's the 3.3 volt side, is an input, and the right side, A5, 5 volt logic, is an output, then you can apply voltage to on the left side, and the correct voltage will come out on the right side. So 3.3 on the left side will convert to 5 volts on the right side. If you switch that, if the right side is an input, right, in it for another maybe pair of pins, 5 volts converted to 3.3 volts. Right? So this is really a cool little circuit. You can use this in both directions. And here's how it works. So when A3, this logic signal, is high, so high means 3.3 volts, right? So we have 3.3 volts right here on A3. That means VGS is 0 volts. Right? If I have 3.3 volts here and 3.3 volts here applied as power, then you could run your KVL equation and you have 0 volts VGS. So your gate to source voltage is 0. And you have, so the MOSFET is off, right? You're below the threshold voltage. That MOSFET is in the off state, I say. There's no connection between drain and source. So what that means is A5 remains pulled a high. It's pulled high through that 10K ohm pull-up resistor because there's nothing effectively connected to the drain here with that MOSFET in the, I'll say, open state. But when you pull A3 low, then VGS is greater than the threshold voltage of the MOSFET. So now A3 is low, 0 volts at source, and you have 3.3 at the gate. Like that's turning on the MOSFET. And what that does is it pulls pin A5 low. So it connects A5 to A3, which is low, it's ground. So you've just shifted the 3.3 volts or 0 volts on the left to the proper logic levels on the right. Okay, so that's going left to right, going right to left. If A5 is low, right, so I pull A5 low, then VS is pulled low through this drain substrate diode, causing VGS to be greater than the threshold. So I have A5 low. You have this, remember that body diode or the drain substrate diode in here? Because of its direction, that's going to pull the source low. So when the source is low and the gate is high, it's going to turn that MOSFET on, and A3 is going to be pulled low. Okay, so a 0 on the right causes a 0 on the left. When A5 is high, VGS is 0 volts, right? Because I have a high voltage here, and VGS doesn't have anything applied across it. So A3 remains high because it's pulled up by A3. So remember, this left side would be an output. I have 3.3 volts applied to gate, 3.3 volts with no current flowing through that pull-up resistor on the left. That means that the source is also going to be about 3.3 volts. Okay, so A3 would remain high because of that pull-up resistor. So this is a clever little circuit to do that. So if you want an integrated circuit solution, there are level shifter integrated circuits available like this. It's right here. So that's another way to do it. And if you're only going one direction from high to low, let's suppose you have a 5 volt output and a 3.3 volt input, then you could use a voltage divider to reduce the voltage. The catch is, though, if you have any kind of significant capacitance on the right side here, because you have those resistors, you might get slow transitions because of the RC time constant. Right? You have current going through a resistor charging a capacitor if there's capacitance on the right. So this won't work for high-speed circuits, but it'll get you by for general purpose logic often. So that's a really simple way to do it. All right, so there's some tricks. If you're interfacing different logic families, different voltages, look at these solutions. And so tuck this slide away for in the future if you're doing a project and you have different logic families that you need to connect together. Okay. All right, so let's switch over from digital to analog. Let's talk about the analog to digital converters in microcontrollers in this case, but in general, actually. So I'll call those either ADCs or you'll see them written as A/D. So an analog to digital converter converts an input voltage, that is an analog voltage, to an integer value. So VAN is an analog input voltage. And inside the microcontroller, or I should say at the output of the ADC, you have an integer value. Okay. And the valid range for the input voltage is called the full scale range. And it usually spans from 0 volts to the full scale range of the ADC. So on the left, the voltage range that will work and give you proper values here would be 0 volts to 1.1 volts if you have a full scale range set for this ADC of 1.1 volts. On the right, the integer value ADC out is proportional to and represents the analog voltage A in. So the right side, you're going to get just a digital value, a binary value inside your microcontroller or at the output of a separate ADC that represents the analog voltage across the whole range from 0 to VFS in this case. So the ADC output, that integer value, has a finite number of values ranging from 0 to n-1. That gives you n values. And its ADC out is usually represented as an m-bit binary number. So where n is 2 to the power of m. So for example, like the ADC you're using in lab, if you have a 10-bit ADC, that 10-bit ADC has a range of 0 to let's see, n-1. Yeah, n-1. So n is 2 to the m, 2 to the 10 is 1024. 1024 minus 1 is 1023. So you have a range of 0 to 1023. That's 1024 values. And the ADC integer value represents quantized values. So that maps the range of the input voltage to those individual values. Each value of the ADC is called a quantization level. So if I'm talking about quantization levels, I'm talking about those discrete levels that are represented by the ADC. So here's an example. Let's take an ADC that has 3 bits of quantization. That would be a very low value. But for an example, to show this, let's use 3 bits. That means you have 8 quantization levels, 0 to 7. If I plot the relationship between the analog input and the digital output, this is what it would look like. So if you divide the full scale into eighths, why eighths? Because there are 8 quantization levels. So here's 0, 1/8, 2/8, 3/8, right? That's a fraction of full scale. And you look at the corresponding values that would be output. So if you're 1/8 full scale, then you'd get a 0, 0, 1 out of it. If you're 1/4, you'd get 0, 1, 0. You could see all the way up here. Okay, so that's very few quantization levels, but you can visualize the mapping between the input of the analog range. Like if you're hovering right around 3/8, you take 3/8 minus a 16th to plus a 16th, that range right there, and you'd map to 0, 1, 1. So this lets you visualize that, but in reality, you usually have more quantization levels. So a 10-bit ADC with a full scale range of 1.1 volts would map values like this. So in the range of 0 to 1.1 volts, that range would map to 0 to 1023. Okay, and usually linearly, it's not really linear, but in this linear fashion like it's shown here. And microcontrollers like the one you're using typically have multiple built-in analog to digital converters. All right, so let's take a look at how these work. Let's take a look at a couple of common examples. There are a few different methods here, but sort of a more intuitive architecture is the flash architecture, also called parallel or direct conversion. And you can think of this architecture comparing the analog input voltage to multiple different voltage levels. So this S/H, that's a sample and hold circuit. So the analog voltage is applied and it might be changing over time, but the sample and hold takes a sample and just holds that value on its output. So on the right here, or where my mouse is, that voltage is held at a constant value of VAN for a short period of time. And then you have this not ladder, but a series of resistors here. So this is a big voltage divider with multiple resistors. Right. So you see that you can get 8 different voltages here. 3, 4, 5, 6, 7. Well, some different voltages here. And so what you're doing, it's actually 7 voltages, because what you're going to do is you're going to compare the input voltage to different steps of voltage created by this voltage divider. So these are comparators. Remember, comparators compare two voltages. We had to talk about comparators. So you pick this comparator right here. It's comparing the input voltage to this voltage between these two resistors of the voltage divider, which is somewhere between Vref and ground, somewhere between Vref and 0. And so this might be a linear distribution, just a regular uniform distribution of voltages here, against which we're comparing the input voltage. And then you can use this voltage to figure out, well, what should the output be? And this is this 8 input to 3 output encoder, which is going to give you the digital value here. So that's going to be a 3-bit output. Okay, so the advantage is this is very high speed conversion. This happens very rapidly. You have this comparison here on the right of the comparators, and then this digital circuit can look at that value and convert it, and you get an output very quickly. But it does require a large number of comparators. Say you have 8 bits, you'd need 255 comparators to make that happen, which may or may not be okay. But as you increase the number of bits, that number of comparators goes way up. And generally, these are larger in size. They require more power from the DC power supply or battery, and they cost more in general. Another way to do analog to digital conversion is to use successive approximation. Okay, so you'll hear that called SAR, successive approximation register. So here's what that looks like. Here's a diagram from this reference. You can take a look at this Circuit Digest web article here. And so here's the input on the left. Here's the binary output on the right. Okay, and so what happens here is we're actually using only one comparator to compare the input against a DAC output. DAC is digital to analog conversion. So this ADC actually uses a DAC, digital to analog conversion, to create a voltage against which to compare the input voltage. And that it can decide, well, is the input voltage higher or lower than the DAC output voltage? So that's what happens here. What happens is this DAC output changes to different levels. So for example, let's suppose the reference voltage here is 10 volts. So this DAC is going to create outputs between 0 volts and 10 volts. So what you might try is, let's use the comparator to compare the input voltage. Let's say it's 5.2. It's 5.2 volts. We're going to compare the input voltage against the DAC's output voltage. And depending upon whether the comparator says that voltage is higher or lower, we're going to change the DAC output voltage. So if Vn is greater than VDAC, let's change the DAC voltage to 7.5. And then let's compare the voltage, compare again, and compare again. And finally, you get to a digital value, right? That DAC value that was creating the voltage, that's the closest you're going to get to the actual analog input voltage. And then you read that as a binary output. All right, so it's a cool way to sense the value, to convert the value of an input voltage using a single comparator and a circuit that looks like this. So generally, this is lower power and higher resolution because you can have more bits to this DAC, but it's slower because this requires multiple cycles to convert the value and complete that conversion. So those are two different ways that ADCs work. There are other ways. There's a pipeline architecture, sigma delta ADCs, other types. But that gives you an idea what's going on, right? What's going on inside the microcontroller. So for the Arduino microcontroller, here's how to use the ADCs. So the Arduino language, again, has these built-in functions to set the pin mode and set the full-scale voltage, which is the analog reference, and built-in functions to read the ADC values. And here are those functions. So you set the pin mode, you set the analog reference, and you set the analog read after the microcontroller knows that this is an input. Okay, so pin mode configures the pin to be an input or an output. Analog reference selects the reference voltage, the full scale voltage for the analog input. And analog read actually performs the conversion. It reads the ADC value for a specified analog pin. Okay, and you can look in the data sheet or any help reference to see a table of specific values for that analog reference. So by default, there's a built-in reference for your microcontroller that you're using on the Wi-Fi Rev 2 board. It's 0.55 volts. That's the default. And then you can set to these other values. Like for your project, you're using the 1.1 volt reference. So you'll see in the code somewhere these values, these words are defined as values, and that value corresponds to 1.1 volts. And the code sets the proper values in all of the low-level registers. So here's an example. Here's an ADC read example. The way to set up the ADC is to set the pin mode, let's say A5. You can go to the pinout diagram and see what header hole has A5 labeled next to it. So you set that pin to an input. Analog reference, I'm setting to 2.5 volts. And starting up the serial port, that has nothing to do with ADC, but I can print the value then to the serial monitor. Then go into the loop, and I'm going to loop and read the analog value every 1 second, roughly. So I declare a variable to store the ADC value. Here's where I actually do the analog read pin A5, and then print out the value. The ADC value is that value. Delay and do it again. So this would print out on the serial monitor of the Arduino IDE the value. So I encourage you to play with this. You know, you have the microcontroller. You can take this code, type it in, copy it in, and just experiment. It's a very useful peripheral for projects. So I took this code and I ran it. I applied a power supply voltage of 1 volt to pin A5. And I ran the code and I could see the ADC value right here. So you get 432, 432, 430, 429. It looks like there's some noise or it's varying a little bit. And here's how you convert that ADC value to an actual voltage. So the analog input voltage, you calculate like this: ADC out, that's the value I read, divided by the number of levels minus 1. That's the range, that's the maximum value that the ADC could output, times the analog reference voltage, in this case 2.5 volts. And so I get 432 over 1023 times 2.5 reference is 1.05 volts. So I'm close. Looks like 50 millivolts off. And maybe my power supply voltage isn't exactly 1.00 volts, but that gets it close. So that's how you use the analog to digital converters in the Arduino. Other microcontrollers are similar. There's different registers to set, different interface code to use. Okay, but what happens if you have two different ranges? You have a full scale range of the ADC, and then you have input voltages that don't match that ADC range. What do? You can use interface circuits. When the measured voltage range, the voltage of, let's say, the sensor or the input you're trying to convert, if that range is not equal to the ADC full scale range, then you need some kind of ADC interface circuit. So for example, let's suppose you're measuring a car battery voltage. So, and you have an ADC with a full scale voltage range of 2.5 volts, so 0 to 2.5 volts. But if you're measuring car battery voltage, you might want to have this, a little wider range. A car battery is typically 12.6 volts, charging voltage 12.8 to 14.1-ish. If you have a high voltage, it might be 15. So let's say you have a 0 to 15 volt range, but your ADC has a 0 to 2.5 volt range. So if you connect these directly together, and you're going to break the chip, most likely. And so you need to take this range 0 to 15 and map it to 0 to 2.5, right? So you want to map the max battery voltage to the ADC full scale voltage. Okay, an easy way to do that is to use a voltage divider. So you take the battery and you create a voltage divider, and you have a lower ADC input voltage compared to the battery voltage. And the ADC voltage then would be VBAT times R1 over R1 plus R2. So you're doing this in lab when you're using the 1.1 voltage reference of the ADC to measure the 6 volt or a little more than 6 volt battery pack. That's what you're doing. But let's suppose you have a low voltage sensor, and you're using a full scale voltage reference of 2.5 volts. So let's suppose that sensor covers 0 to 0.5 volts. Right, and your ADC full scale range is 0 to 2.5 volts. Okay, so you want to map like this. You want to map the max sensor voltage to the max ADC voltage. Okay, so what you could do is amplify input voltages to get better measurement resolution. So right here, it'll work if you sense using a 2.5 volt reference ADC and connect it directly to this range. You'll be able to measure, right? You won't blow out the ADC, but you're not going to get the highest resolution of the sensor output that you could. So let's use an amplifier to achieve better measurement resolution. So the ADC voltage resolution is like each increment of the ADC output value, right? What does that correspond to in terms of the quantized voltage levels at the input? Right, so the ADC resolution Q is the full scale range divided by N, which is full scale divided by 2 to the M, 2 to the number of bits of resolution of the ADC. So for a 10-bit ADC with a full scale voltage of 2.5 volts, 2.5 or 1023, 2.44 millivolts. So you could go back to, remember op-amp circuits, go back to circuits class where I said these are useful. Well, they are useful because you could take this low voltage sensor, amplify that output, and then apply that output to the input of the ADC. And so this is a non-inverting amplifier made from an op-amp. So VADC is Vsense times this gain here. And what this does is this expands the range, right? Expands that range of the ADC over which the sensor voltage spans. So you get a better resolution. Okay. And as you're doing in lab, you often use, if you have a slowly varying input voltage, you can use capacitors for filtering on the input voltage near the ADC when these voltages change slowly. All right, so let's do a clicker on ADC resolution. Let's use a temperature sensor, just like you're doing in lab. You have a temperature sensor that has an output voltage that ranges from 0 volts to 1 volts, and that covers minus 50C to plus 50C. Here's the plot here, right? 0 to 1. And you're using an 8-bit ADC with a full-scale input value of 1 volt to sample that temperature sensor voltage. So minus 50C is 0 volts, plus 50C is 1 volt, and you're going to sample that with an 8-bit ADC, full-scale range, 0 volts to 1 volt. Right, so we're matched there. So what is the temperature resolution in Celsius of the measurement. So, when the ADC ticks up one value, what is that change in the measured temperature? Give that a shot. Okay, so here's how I work the problem. Right, the resolution is VFS over M over N, which is VFS over 2 to the M. So that's 1 volt over 256, which is 3.906 millivolts. So what does 3.906 millivolts correspond to in temperature change? Well, it's a 100-degree span mapped to a 1 volt span. So we get 0.4 degrees C. Okay, so the answer is 0.4. And notice if the full scale range were 5 volts, the resolution would be 2 degrees C, which would be a really poor resolution. So if I had the full scale range set to 5 volts, you'd have a 2 degrees C resolution. That's a pretty crummy, in my opinion, temperature sensor resolution. 0.4, I think, is more reasonable. Or you could use an amplifier to improve the temperature resolution, but you'd have a reduced temperature measurement range. Okay. So lots of ways to do this. Change the full scale range, add amplifiers, add voltage dividers just to get your ranges mapped over the span of the sensor value you want to cover. So we've been talking about sampling DC or slowly varying signals. Sampling AC signals using ADCs takes another step in the theory. If you're sampling audio or radio frequency, or you're detecting optical signals, or you have sensors with rapidly varying outputs, that's what I mean by AC signals. And I would love to cover those, but unfortunately, we don't have enough time in this class to cover that sampling theory. So we're not going to cover that, but I have a couple leads for you to follow if you do want to learn more about this. Okay, so some good things to know, some takeaways are this. You might have heard of the Nyquist sampling theorem, or Nyquist. Nyquist tells you how fast or how rapidly or at what rate you have to sample for a given AC signal. So you must sample at least twice the highest frequency of the signal for what we call baseband sampling. And if you don't do that, you get aliasing. So in other words, if I have these dots, I can't tell if it's the pink signal or the dotted black signal. I can't tell which I'm trying to represent with those dots. That's called aliasing. But if you sample fast enough for a given limited bandwidth, given limited highest frequency, then you can uniquely identify the frequency of the signal and the signal itself. Or for something called bandpass sampling, you can actually sample at just more than twice the signal bandwidth. So if you have actually a signal at a higher frequency, you could sample at twice its bandwidth and you get it translated down to the DC range. So something else you could look at. Or otherwise you get this aliasing effect. One thing to pay attention to is that AC signals often have 0 DC offset. So if you're sampling with an ADC that has like a 0 to 1 volt range, then you have to apply an offset so that you center that AC signal somewhere around the center of the ADC range. So AC signals with 0 offset usually need a DC offset applied, as shown here, to sample using an ADC with an input range of 0 to FS. There's a whole lot to say about this, but information on sampling AC signals can be learned if you study just the intro parts of DSP topics. So you can find a textbook, I'd find a web page describing this, and you can learn these topics and sample AC signals, like audio signals. Okay. All right, well, I've gone over my time just a little bit. So in closing, homework 5 is posted. Take a look at that on Canvas. Also check Canvas for the upcoming lab schedule and other due times. I will hold office hours in just a few seconds. So if you'd like to join, please join. If not, I'll see you next time. Have a great night.